Section 24.8 Qualitative Molecular Orbital Theory for Conjugated and Aromatic Molecules, the Huckel Model. So it's possible to hand calculate the molecular orbital energies for conjugated systems, such as 1,3-butadiene, 1,3,5, hexatriene or benzene or some other conjugated networks. So really you just need to solve the Schrodinger equation for the conjugated electrons in the system. Let's look at 1,3-butadiene. We will focus on the 4 p electrons, one contributed by each of the 4 carbon atoms. And then we can write out these 4 linear equations. C1, C2, C3, C4 are the molecular orbital coefficients. H11, H22, H33, H44, they are called Coulomb integrals, but they are really the atomic orbital energy of the 2p electron in the carbon atom. You can simply look up the ionization energy of the carbon atom and put a negative sign in front of it. You get this H11, H22, H33, H44. The mathematical form of H11 is the integral of phi 1 times the Hamiltonian being applied to phi 1. All right? So phi 1 is simply the 2p orbital of a carbon atom. H12, it's called the resonance integral. The mathematical form of this one is the integral of phi 1 times the Hamiltonian being applied to phi 2. So really it's the 2p orbital of carbon 1 times this Hamiltonian being applied to the 2p orbital of carbon 2. So over here this is between 1 and 3, and then 1 and 4, 2 and 1, 2 and 2, 2 and 3, 2 and 4, etc., etc. I want to say this H12 is roughly 5 to 15% of H11 in this situation and in many other conjugated networks. All right, so this resonance integral is usually much smaller than the Coulomb integral. This Coulomb integral is roughly the atomic orbital energy, and this resonance integral is give you the interaction between 2 atomic orbitals centered on 2 different nuclei. So that's why this is much smaller, usually 10% of H11. H13 in 1,3-butadiene, this gives you the interaction between the 2p orbital on carbon 1 and the 2p orbital on carbon 3. I would say this is just 0 or negligible. Between carbon 1 and carbon 4, it's roughly 0. So this H14 is even smaller than this H13 because the distance between carbon 1 and carbon 4 is longer than the distance between carbon 1 and carbon 3. So only here H12 is roughly 10%, between 5% to 15% of H11. S11, S22, S33, S44, those are just the overlap integrals between the 2p orbital on carbon 1 and itself. This S21 is the overlap between the 2p orbital on carbon 2 and the 2p orbital on carbon 1, so etc. Again, HAA, so when these 2 numbers are the same, it's the Coulomb integrals. We're looking at just one single carbon. HAB are called resonance integrals. That gives you a rough idea about how much 2 atomic orbitals centered on different nuclei interact with each other. So by just looking at this H42, I think this is nearly 0. H41 is nearly 0 because if you imagine the molecular structure of 1,3-butadiene, the distance between carbon 1 and carbon 4 is really long. It's very hard to just solve 4 linear equations, but we can convert that to a linear algebra problem. So we're just have to kind of just make sure the value of this determinant is 0. And we use SAA equals 1, SAB equals 0. This is a approximation. We're just assuming the overlap between the two p orbitals centered on different nuclei is simply 0. And we have HA equals alpha, HAB is beta. Both alpha and beta are negative. So alpha is simply the 2p atomic orbital energy in a free carbon atom. And beta will give you the extent of the interaction, the constructive interference between two p orbitals centered on two different nuclei. All right, but again, if A and B differ by 2 or more, that means the two carbon atoms are really far away from each other, and then beta is simply 0. So that's why we got this equation. This is again a linear algebra problem to have this determinant to be 0. We solve this equation. Again, this is 0 only because the distance between carbon 1 and carbon 3 is really long. It's even longer between carbon 1 and carbon 4. All right, so that's the reason. This 0, that's because the distance between carbon 2 and carbon 4 is really long. This is between carbon 1 and carbon 3, between carbon 1 and carbon 4. So the diagonal terms are just alpha minus epsilon, alpha minus epsilon. The off diagonal terms, you see some zeros if the carbon atoms are far away from each other. But for the carbon atoms that are only one bond away from each other, you need to put a beta here. Again, beta is the so-called resonance integral. Beta is really important because it is beta that gives you the bonding energy. So you need to know how to expand this 4x4 determinant into a total of 4 factorial terms. Fortunately, many of those terms are equal to 0 because of the existence of those zeros. So really, after you expand this, you'll get a polynomial equation of epsilon, and then you solve this equation, you will get 4 roots or 4 solutions or 4 numbers for epsilon. And those are the corresponding molecular orbital energies. So from here to here, I just did some algebraic simplification. To make things easier, I set x to be alpha minus epsilon squared, and then we can reduce this 4th order polynomial equation to a quadratic equation, and we solve that, we get the value of x, and then alpha minus epsilon is the square root of x. In particular, it can be plus or minus square root of x. So we got these numbers, and then we solve for epsilon. Again, epsilon is the molecular orbital energy. We have 4 different numbers. That means we have 4 different molecular orbital energy levels. From alpha plus 1.6 beta, alpha plus 0.6 beta, alpha minus 0.6 beta, and alpha minus 1.6 beta. Remember, alpha and beta are both negative. Alpha is the 2p atomic orbital energy in a free carbon. So alpha is a negative number. I think alpha is negative 10 electron volts, roughly. If you look up the ionization energy of carbon, it's positive 10 electron volts. That means it takes some external energy of 10 electron volts to promote this electron from a atomic orbital with negative 10 electron volt energy to 0 electron volt. All right, so alpha is roughly negative 10 electron volts, if I remember the number correctly. Beta is usually between 5% to 10% of alpha, so I think beta is just roughly 1 electron volt from my vague memory here. And then all you need to do is you need to rank this 4 molecular orbitals in the increasing energy order. So from bottom up, the energy increases, or the energy becomes less negative. And then you can put 2 electrons in here, 2 electrons in here, right? So you put the electrons into the lower energy orbitals first. All right, so put the electrons, 2 pi electrons here, and then 2 pi electrons here. This is your HOMO, and then this is your LUMO. This is LUMO plus 1. This is HOMO minus 1. I'm going to show you the entire molecular orbital diagram here by putting everything on one page. All right, so there are 4 orbitals. 1, 2, 3, 4. 4 molecular orbitals. They are constructed from the 4 atomic orbitals, 1 on each carbon. All right, and this shows you the conjugation. Over here, there's 1 nodal surface, 2 nodal surfaces. Over here, there are 3 nodal surfaces. 1, 2, 3. So 0 nodal surfaces, 1 nodal surface, 2 nodal surfaces, and 3 nodal surfaces. And energy goes up. There's a typo here. This is 1.62 beta, okay, not 0. So obviously, there's a mistake here. Now you can calculate the total energy of this 4 pi electrons. So it's going to be just alpha plus 1.62 beta times 2, because you have 2 electrons here, and then alpha plus 0.62 beta times 2. You put them together, you get this much energy. What if you have just 2 separate carbon-carbon double bonds? What if there's no conjugation at all? In that case, the total energy of the 4 pi electrons without conjugation is 4 alpha plus 4 beta. So if you compare these 2 numbers by forming the conjugation network, the energy is further decreased by 0.472 beta. So we are comparing this number with conjugation and this number without conjugation. So this 4 beta comes from just 2 separate carbon-carbon double bonds. So this is the resonance energy or conjugation energy. I think beta is negative 1 electron volt. So, but I might be wrong. This additional resonance energy make the conjugated system, such as 1,3-butadiene, more stable. All right, let's talk about 4 separate carbon atoms. The energy of the 4 2p electrons, 1 from each separate carbon atom, is just 4 alpha. All right, that's just 4 alpha. Okay, so alpha for each 2p electron. 4 such electrons, you get 4 alpha. But then if you can form 2 double bonds, the energy is decreased to 4 alpha plus 4 beta. And now if you form conjugation, it's 4 alpha plus 4.472 beta. Now let's look at benzene. We can solve the molecular orbital energies for benzene using a similar algorithm. You need to make a 6x6 determinant to describe the interaction among these 6 pi electrons mathematically. And you set that determinant to 0. You solve the determinant. You set you get the molecular orbital energies. You will get alpha plus 2 beta, alpha plus beta, alpha plus beta. So you have 2 degenerate MO over here. And then alpha minus beta, again, 2 degenerate molecular orbitals. And then alpha minus 2 beta. We always place electrons in the lower energy orbitals first. So that's how we do it. And then you can calculate the total energy of this 6 pi electrons. It's alpha plus 2 beta times 2, and then alpha plus beta times 2, and then alpha plus beta times 2. So in total, I think you will get 6 alpha plus 8 beta. All right, 6 alpha plus 8 beta. What does that mean? Well, with this conjugation taken into account, we get additional resonance energy of 2 beta. So this is further stabilization because, again, beta is negative. All right, so there's a 4m plus 2 rule in organic chemistry for you to determine if a conjugation network is aromatic or anti-aromatic. So in this case, it's aromatic when you have 4n plus 2 electrons. When n is 1, you have 6 electrons. So if you have a conjugation network in a ring, so like in here, a 6-member ring, when you have 6 pi electrons, it's aromatic. And then when you have 10 electrons, it's aromatic. When you have only 2 electrons, it's aromatic. But when you have 4 electrons, when you have 8 electrons, it's anti-aromatic. So these molecules tend to distort their planar structure to remove this anti-aromacity, all right, to further reduce its energy. So let me give you another example. This carbon 3H3 plus. So basically, you just have a 3-membered carbon ring. Each is bonded to a hydrogen, and you have just one double bond in this 3-membered ring. What about the third carbon? The third carbon has a +1 charge. So in this ring structure, you have 2 pi electrons, so this is aromatic. But in C4H4, in C8H8, they all have 4n pi electrons, and they are anti-aromatic. I believe in this molecule, the structure is non-planar. It's just to remove this anti-aromacity. In this structure, I cannot remember whether it's planar or non-planar because this ring is so small. And sp2 hybridization prefer the planar structure, right? So I can't remember for sure, but I can be sure that the 2 double bonds in this molecule do not have any conjugation, all right?